Okay, in this video I'll be solving this question from JEE Advanced 2025 using Lagrangian mechanics. So let's first read out the question. It says that the center of a disk of radius small r and mass small m is attached to a spring constant k inside a ring of radius capital R greater than small r as shown in the figure. The other end of the spring is attached on the periphery of the ring. Both the ring and the disk are in the same vertical plane. The disk can only roll along the inside periphery of the ring without slipping. The spring can only be stretched or compressed along the periphery of the ring following the Hooke's law. In equilibrium, the disk is at the bottom of the ring. Assuming small displacement of this disk, the time period of oscillation of center of mass of the disk is written as T is equals to 2 pi by omega. The expression for omega is. So it's a really simple question, and the analytical solution is way more easier than the Lagrangian method. But since it's just basically a video on how to apply Lagrangian mechanics on certain questions of like mechanics, so here it's also really easy. And of course you might know that in Lagrangian mechanics you just need to know two things. First is the kinetic energy of the system. It's the kinetic energy of the system, and V is the potential energy of the system. Once you know these two quantities, you can derive the equations of motion using just these two. Yes, so let's just find out the kinetic energy and potential energy for this question. Let's first draw the diagram. We have a ring of radius capital R, and inside that we have a disk of radius small r. It is attached with a spring of constant k. Its radius is small r. Radius of this bigger circle is capital R. Okay, now we'll try to find out the kinetic energy and potential energy of the system. So this total distance is r. This total distance is also r. So this much distance, this is equal to r minus r. Fine. Let this angle be theta. Okay, so let's say the disk rolls from here to here, from this point to this point. So this is gonna be your x, or the elongation of the spring. It is given that x is very small displacements are happening. So a few equations that I can write from the given information is that x is gonna be equal to r minus r times theta, because this is gonna be your x and this is equal to r minus r times theta. Another information that is given in the question is that it is rolling without slipping. Okay, it's given that the disk can only roll without slipping. So that gives me another equation that the velocity of this disk is equal to VCM is equal to the omega of this. Let's say it's omega dash times r, and let the omega about this axis be omega. And so I can also write that VCM, it's also equal to omega times r minus r, this omega times this distance. Okay, so basically here's the center, here is the disk, it's moving along this. It has VCM. This is the basically tangential velocity along this. If it's performing a circular motion like this is the tangential velocity. This is going to be equal to omega, which is omega around this point O, and the distance between the center and this center, which is equal to r minus r. So VCM is equals to this, and the other condition that the rolling without slipping is happening, that gives us this, that VCM is equals to omega dash times R. From this, what we get is omega dash is equals to omega R minus R upon R. These are the only two conditions that we need. Now we can go and write our kinetic energy and potential energy. Let's first write the kinetic energy of the system, which I denote by T. So it has two velocities, right? So it has like half m VCM square. One is this, and it also has rotational energy half I omega dash square. So VCM we already have calculated. It's equal to omega times R minus R square plus half I, the moment of inertia of a disk, is nothing but it's equal to mr square by 2. And omega dash square also we calculated. Omega dash is nothing but omega times R minus R upon R. So we substitute that over here. Omega square R minus R square upon R square. So R square gets cancelled out. What we are left is half m omega square R minus R square 1 plus 1 by 2, which gives us 3 by 4 m omega square R minus R whole square. This is the kinetic energy of the system. Now we write the potential energy. So it's fairly simple to see that the system has two potential energies. One is the potential energy caused by this spring, which is equal to nothing but half kx square, and another is the gravitational potential energy. So let's assume that this point is zero potential energy, and this distance, this is going to be equal to r minus r times cos theta. So the potential energy at this point is going to be equal to minus mg r minus r cos theta. So these are the two potential energies that we have. We add them together, we get half kx square minus mg r minus r cos theta, and x, as I already told you, is equals to r minus r times theta. So v is nothing but half k r minus r whole square theta square minus mg r minus r cos theta. So now we have the potential energy and we have the kinetic energy. We have both the quantities. Now it's fairly simple to calculate the equations of motions. We just have to put them together. Okay, now we'll write the Lagrangian for this system. As we know that Lagrangian is nothing but kinetic energy minus potential energy. So let's just write it down. L is equals to 3 by 4 m omega square r minus r square, yes, minus half k r minus r square theta square plus mg r minus r cos theta. Now we have the Lagrangian. Now just I have to plug in into the Euler-Lagrange equations, and we have the equations of motions. So we know that from the Euler-Lagrange equation that del L by del theta is equals to d by dt of del L by del omega. So let's just solve this. So del L by del theta, it's gonna be equal to minus 2, and 2 gets cancelled out by 2. We have k r minus r square theta, and again a minus mg r minus r times sine theta. That gives me nothing but minus of k r minus r whole squared theta plus mg r minus r sine theta. And well, since the x is very small, so I can approximate sine theta by theta. So I have k r minus r squared plus mg r minus r theta common taken out. And now let's calculate d by dt of del L by del omega. It's gonna be equal to d by dt of, this is your del L. Del L by del omega is gonna be 3 by 2 m r minus r square omega. So d omega by dt, it's gonna be equal to alpha times alpha. So I just have to equate them both together. I have 3 by 2 m r minus r square alpha is to minus of k r minus r square plus mg r minus r theta. That gives me alpha as minus 2 by 3 of k by m plus g by r minus r times theta. So this is your omega squared. So we have our final answer, that omega is equals to this a. Omega is equals to root 2 by 3 g by r minus r plus k by m. So thank you for watching. Do subscribe.